Okay, so I'm just going to try to go over once more the flip-flop because there was a little bit of confusion, I thought, at the end of recitation today, and I wanted to clear it up. So this is the basic flip-flop circuit. So there's two lines. There's the data line and a latch line, and the basic idea of the circuit is that it's going to output D when L is high, and then it's going to output the last state of D when L transitions from high to low. So it's going to transmute the date when L was high. It's going to sort of lock in that state. So if you imagine kind of a picture where you have a data line that might be going up and down, and then you have this latch line. I'll grab another color. So that's our data line in black. And then you have a latch line. And whenever the latch goes low, then it freezes D so that at that point Q is equal to 0, and it's going to stay that way forever. Whereas before that point, Q was going up and down with D. So the output is Q is going to be D when the latch was high. When the latch goes low, it latches in the final value, and it sort of stores that value at the output. So let's see how that works. So first of all, let's try to analyze the circuit. Let's assume D is high. So let's suppose first of all that D is high. All right, we'll do this whole argument in purple. Sorry, L is high is what I mean. L is high. If you go down here, D is high. L is high means that when L is high, the output just follows D, and let's prove that. So this L is high, so L is 1 here and here. So the output is just going to be D bar. If you take the naught of D as the input, you're going to get the naught of D as output. And then over here, you're going to get D as the output. If we say that these two lines are X and Y, we don't know yet what they are, that's fine. We can say that Y is going to equal X nor D bar, and X is going to equal Y nor D. So we can actually take this expression and plug it in, for this expression for X, and plug it in there. So you're going to get that Y is equal to YD nor like that. And now we can use De Morgan's theorem on this, and we get Y plus D ANDed with D. All right, because we get Y plus D naught plus D naught. So it's just Y plus D ANDed with D. Now, these two, this has to equal Y. So now we can try to solve that for Y. So now we have an expression for Y. We can try to solve it. Well, the D distributes in, so we just get YD plus DD equals Y. And the DD, any number and itself, is always going to just equal the number, right? So if it's 0, it'll be 0 and 0, and you'll get 0. If it's 1, it'll be 1 and 1, and you get 1. So that'll just be D. And then here you'll get YD. And now the D will distribute out, and you get Y plus 1 ANDed with D. But y plus 1, anything ORed with 1 is always going to be 1, and 1 and a number is always going to just be the number. So that means that y is equal to d. So that means that Q is equal to D, and correspondingly, X is going to be D plus D all knotted. Well, D or D, if it's 0, then it's going to be 0. If it's 1, then it's going to be 1, so it's just D knotted. So indeed, that's equal to Q bar. So we've proven that the data, that when L is high, the data just flows through. Okay? So I'm going to write that down just to emphasize it. When L is high, the data flows through. Okay, now let's think about what happens when the latch drops. Okay? So if the latch drops, let's pick a different color to do that in. So let's pick orange. I hope that's different enough to be clear. So when the latch drops, so we're going to have the latch be 0 now. Well, anything added with 0 is going to be 0. So we're going to have 0 here and here. So just before this dropped to 0, we had D, and let's call that D prime, and D bar prime, because these were present because the latch had been high previously, and we just agreed that it outputs D and D bar when the latch is high. So D prime and D bar prime, or maybe we can imagine it's like D at T minus epsilon, something like that. Now, if we have D ORed with 0, right, anything ORed with 0 just gives itself. And then we take the NOR, and so we're going to get itself bar, right? So that's consistent, at least. So this time scale is consistent. And then this knotted value, this D bar knot, NORed with 0, is also going to give its knot. So actually, even though we changed this input, we don't change the output. So remarkably, when L transitions to low, the output is unaffected. Stays equal to D at T minus epsilon prior to the transition. So in this way, the latch has locked in the prior values of D and D bar, and they won't change until the latch value raises to 1, at which point this previous argument applies again. So I hope that's helpful. At the end of recitation, we ran out of time a little bit to go through that discussion. Feel free to email me any questions you might have. Okay, thanks.